How much strain can one of the world's most active plate boundaries absorb before it shifts again? How much warning can an offshore rupture provide when the seafloor moves near the Japan Trench? And when a major quake strikes beyond the coastline, how quickly can authorities determine whether the next danger is strong shaking, a tsunami, or a larger aftershock sequence waiting to unfold? Those questions sat at the center of the urgent hours after a powerful magnitude 7.4 earthquake struck off the coast of Honshu, near Miyako, on April 20th, 2026 at 7:53 UTC. The United States Geological Survey located the event 100 kilometres east-northeast of Miyako at a depth of 35 kilometres, describing it as a reviewed magnitude 7.4 earthquake with strong shaking potential. The location mattered as much as the magnitude. This part of northeastern Japan sits on one of the planet's most closely watched plate boundaries, where the Pacific Plate dives westward beneath the North America Plate along the Japan Trench. In the USGS technical analysis, the quake was identified as thrust faulting near the subduction interface, with moment tensor solutions consistent with east-west compression expected in the region and with slip occurring along the plate interface. The agency also noted that at this location the Pacific Plate moves roughly westward relative to the North America Plate at about 83 millimeters per year, or about 3.3 inches per year, a pace that helps explain why this stretch of ocean floor repeatedly stores and releases enormous amounts of tectonic energy. That tectonic setting is not an abstraction. It is the reason Japan's northeast coast remains under constant seismic scrutiny. The region around Miyako has produced many large earthquakes over time, and the USGS said that within 250 kilometers of this event, 36 earthquakes of magnitude 7 or larger have occurred in the past 100 years. The April 20th rupture also occurred 192 kilometers north of the March 11th, 2011 magnitude 9.1 Tohoku earthquake, the event that generated the deadly tsunami still remembered across the Pacific. The USGS put the likely size of the slip zone for this magnitude event at roughly 70 kilometers long by 35 kilometers wide, underscoring that earthquakes are not just points on a map, but physical ruptures across broad fault surfaces. Within minutes, the earthquake triggered a tsunami warning. Reuters reported that waves of up to 3 meters were forecast in the initial alert, while the Japan Times said the warning was issued for Iwate, Aomori, and Hokkaido. The warning was later lifted and downgraded after only smaller waves were observed, including a reported peak of 80 centimeters, or about 2.6 feet, before the alert was eased. Even so, the first response showed how quickly Japan's warning system moves when an offshore thrust earthquake strikes within a subduction zone that has a long history of tsunami-generating events. The initial public response followed a familiar but serious pattern. Reuters said evacuation orders were issued in towns including Otsuchi and Kamaishi, communities with direct memory of the 2011 disaster. Rail service, including bullet trains, was disrupted and highways were closed temporarily as officials moved to reduce exposure along the coast and in transportation corridors. Reuters also reported no immediate casualties or major damage in the first phase after the quake, while government officials said nearby idle nuclear power plants showed no abnormalities. Those details reflected a response system designed for speed, issue the warning first, verify impacts next, and keep the public out of the lowest-lying areas until the threat is better understood. At the same time, the quake immediately raised a second question that often follows major offshore ruptures in Japan. Was this the main event, or could something stronger still follow? The Japan Times reported that authorities issued a rare special advisory over the chance of a larger earthquake, noting that the probability of a magnitude 8 or stronger event was higher than usual, though still around 1% or about 10 times the normal background level of roughly 0.1%. Reuters reported the same warning in different terms, saying the risk of an earthquake of magnitude 8 or more over the following week had increased to about 1% from a usual 0.1%. That is a small probability in absolute terms, but in the context of a densely populated and highly seismic country, it is the kind of number that immediately shapes public behaviour. The possibility of a larger rupture is not a speculative talking point in this setting. It is part of how Japanese authorities communicate risk after major offshore earthquakes. The concern arises because large subduction zone events can alter stress along adjacent segments of the plate boundary. In practical terms, that means one strong thrust event can sometimes be followed by additional strong shaking in nearby patches of the same system. The USGS, while not issuing a public policy warning in the way Japanese agencies do, framed the event as a plate interface thrust rupture in an especially active part of the Japan Trench system. The broader implication is clear. The earthquake was not an isolated surprise, but another release from a boundary that is continuously loading, locking and slipping beneath northeastern Honshu. The oceanic setting also shaped the tsunami response. Offshore thrust earthquakes are among the most likely to deform the seafloor in a way that displaces water, which is why warnings can be issued quickly even before full damage assessments are possible. In this case, the warning reflected both the magnitude and the geometry of the rupture. The USGS and Reuters descriptions are aligned on the key physical fact that this was a shallow to moderate depth event on or near the plate interface, the kind of structure that can transmit force efficiently to the sea floor. That is the reason officials treat such earthquakes differently from deeper inland quakes of similar size. The warning also came against the backdrop of Japan's recent seismic experience. Reuters noted that the quake came after the country had already been dealing with other notable tremors in 2026, including a magnitude 6.2 event in western Japan in January and a magnitude 5 earthquake near Tokyo in early April. The country's seismic calendar has therefore remained busy, but the Miyako event stood apart because of its offshore location, its thrust mechanism, and its direct relevance to tsunami preparedness. It was not simply another inland jolt felt in office towers and apartment blocks. It was the kind of rupture that forces emergency authorities to think about coastal evacuation, harbour exposure, transport disruption, and the possibility of a wider aftershock sequence. There was also an important geological nuance in the USGS readout. The agency noted that the region is sometimes described through the lens of smaller microplates, including the Okhotsk and Amur microplates, which are often treated as part of the larger North America and Eurasia systems, respectively. That matters because the northeast Japan margin is not a simple two-plate boundary in practice. It is a zone where local tectonic blocks and larger plate motions overlap. For this reason, the same offshore rupture can be discussed in both broad and local tectonic terms. At the broadest scale, the Pacific plate is subducting beneath the continental margin. At the local scale, the motion is partitioned among microplates that help explain the exact directions and rates of deformation seen in the region. The scale of the event was sufficient to be felt widely, though the strongest consequences were concentrated in the alert phase rather than in documented destruction. The USGS shake map listed strong shaking for the earthquake, and the event appeared among the agency's significant earthquakes list for the period. That classification reflects both the magnitude and the expected impact footprint. When a magnitude 7.4 quake occurs offshore at 35 kilometres depth, the immediate concern is not only what was shaken on land, but how the seabed itself moved, how much stress remains on the surrounding fault network, and how coastal communities should respond in the next hours and days. The broader historical record adds more weight to the event. The USGS emphasized that this segment of the Northwest Pacific margin has hosted many larger earthquakes over the last century, making it one of the most active and closely monitored seismic regions in Japan. The area's proximity to the 2011 disaster keeps it especially sensitive in public memory, but the concern is not limited to history. It is rooted in the present-day geometry of convergence, in which the oceanic plate keeps pushing beneath Japan at a measurable annual rate. In that sense, the April 20th quake was both a sudden event and the visible outcome of a very long process. By late Monday local time, the immediate tsunami alert had been eased, but the larger question remained open: what would the aftershock sequence reveal about stress still moving through the fault system beneath the Japan Trench? That is the point at which the morning's technical data becomes the framework for the next hours of monitoring, and where the next part of the report turns from the first shock and the warning response to what the event may mean for the broader seismic picture around Honshu, Miyako, and the offshore plate boundary. The hours that followed the offshore rupture did not unfold as a single contained event, but as a sequence of measurements, updates, and recalibrations across Japan's monitoring networks. Aftershocks began to populate the same offshore corridor east-northeast of Miyako, tracing out the portion of the plate interface that had just slipped. Each additional tremor, whether barely perceptible or strong enough to register across coastal communities, added detail to a rapidly evolving map of stress redistribution beneath the seafloor. This pattern is typical for a thrust earthquake of this scale, where the main rupture relieves accumulated strain in one segment but transfers force to adjacent areas along the same boundary. The geometry of the rupture zone provided early clues about how that redistribution might unfold. A fault plane extending roughly 70 kilometres in length and about 35 kilometres in width represents a substantial patch of the subduction interface, yet it occupies only a fraction of the broader system that stretches along the offshore margin of northeastern Honshu. That distinction matters, because the Japan Trench is not a single continuous surface that releases energy in one motion. Instead, it behaves as a segmented boundary, where some areas remain locked while others slip episodically. The April 20th event illuminated one of those segments, but it also sharpened focus on the neighbouring stretches that did not rupture at the same time. Attention naturally shifted to the relationship between this event and the legacy of the 2011 Tohoku earthquake and tsunami. The two events are separated by nearly 200 kilometres, yet they occupy the same tectonic system, governed by the westward motion of the Pacific Plate as it descends beneath northeastern Japan. The earlier catastrophe demonstrated how a massive rupture across multiple segments of the plate boundary can produce both intense ground shaking and a devastating tsunami. By comparison, the April 20th earthquake was smaller by several orders of magnitude in energy release, but it occurred within the broader stress field shaped by that earlier megathrust event. That connection does not imply a direct causal chain, but it does frame the newer quake as part of a longer sequence of strain accumulation and release along the same subduction margin. In practical terms, the distinction between a magnitude 9 class event and a magnitude 7 class event is not merely numerical. It reflects differences in rupture length, slip magnitude, and the volume of displaced seawater. A magnitude 7.4 earthquake can generate hazardous conditions, including localized tsunami waves and strong coastal shaking, yet it typically involves a more limited rupture footprint than a megathrust event. The observed wave heights following the April 20th quake, which peaked below 1 metre in many monitored locations, were consistent with a moderate displacement scenario rather than a basin-wide tsunami. That outcome reinforced the importance of rapid detection systems that can distinguish between a large but contained rupture and one with far-reaching oceanic consequences. Monitoring agencies continued to refine their models as additional seismic data streamed in. Moment tensor solutions, waveform inversions, and aftershock distributions all pointed toward a thrust mechanism aligned with the compressional regime of the Japan Trench. The orientation of slip, broadly consistent with east-west compression, matched expectations for a boundary where the oceanic plate is being forced beneath a continental margin. This alignment is not incidental. It is the mechanical expression of plate convergence that has persisted over geological timescales. Each recorded earthquake in the region serves as another data point in understanding how that convergence is accommodated, whether through steady creep, intermittent locking, or abrupt rupture. The presence of microplates added another layer of complexity to that interpretation. The boundary in question is often described in terms of interactions between the Pacific Plate and the North America Plate, yet regional models also incorporate smaller tectonic blocks such as the Okhotsk and Amur microplates. These subdivisions help explain variations in motion, stress orientation, and seismic behavior across northeastern Japan. In the context of the April 20th earthquake, they underscore why localized deformation patterns may not always align perfectly with broader plate-scale models. Instead, the observed rupture reflects both large-scale convergence and finer-scale structural heterogeneity within the overriding plate. As the aftershock sequence expanded, authorities maintained a heightened level of alert, particularly along coastal zones. Even after the formal tsunami warning was lifted, advisories remained in place for a period, reflecting the possibility of delayed or secondary wave activity. Coastal infrastructure, including ports, seawalls, and evacuation routes, was reassessed in real time. Transport systems that had been temporarily halted during the initial alert gradually resumed operation, but not without precautionary inspections. Rail lines, highways, and utility networks underwent rapid checks to ensure that no hidden damage had compromised their integrity. This layered response illustrates how a single offshore earthquake triggers a cascade of operational decisions across multiple sectors. The question of whether a larger earthquake could follow remained central in the days immediately after the event. The probability estimates communicated by authorities, around 1% for a magnitude 8 class earthquake within a week, did not signify an imminent disaster. Yet they represented a measurable increase over baseline conditions. Such figures are derived from statistical models that incorporate historical seismicity, stress transfer calculations, and real-time observations of aftershock behavior. While the absolute probability remains low, the relative increase is sufficient to influence preparedness measures, particularly in a region where infrastructure and population density amplify the consequences of any major seismic event. In coastal communities near Kamaishi and Otsuchi, the response carried an additional dimension shaped by lived experience. These towns were among those affected during the 2011 disaster, and their evacuation protocols, warning systems, and public awareness campaigns have been refined over the years since. The swift movement of residents to higher ground during the April 20th alert reflected not only official directives, but also a deeply ingrained understanding of coastal risk. Even in the absence of a large tsunami, the act of evacuation itself is treated as a necessary precaution rather than an overreaction. Further north, in Hokkaido and Aomori Prefecture, monitoring stations tracked both seismic and sea level changes as part of a coordinated regional response. The integration of these data streams allows for near real-time assessment of evolving conditions, reducing uncertainty in the critical minutes and hours following an offshore earthquake. Tide gauges, ocean bottom pressure sensors, and coastal observation points collectively contribute to a dynamic picture of how the ocean responds to seafloor deformation. In this case, the data confirmed that the initial warning, while justified by the earthquake's characteristics, could be safely downgraded once observed wave heights remained below critical thresholds. The physical characteristics of the rupture also influenced how energy was transmitted through the surrounding crust. A depth of 35 kilometres places the event within the upper portion of the subduction interface, where the interaction between plates is capable of generating strong ground motion onshore. However, the offshore location meant that much of the immediate energy dissipation occurred beneath the ocean, reducing direct structural impacts on land compared to a similarly sized inland earthquake. This distinction is critical when assessing potential damage patterns, as offshore events tend to shift the primary hazard from ground shaking to tsunami generation, while inland events concentrate their effects within built environments. Seismologists continue to analyze waveform data to refine estimates of slip distribution across the fault plane. Variations in slip can indicate areas where stress was more fully released versus zones that may remain locked or only partially ruptured. These details, while technical, have practical implications for forecasting aftershock behavior and assessing the likelihood of further significant events. A heterogeneous slip pattern, for example, may leave pockets of elevated stress that could be released in subsequent earthquakes, whereas a more uniform rupture might reduce immediate aftershock intensity but still leave adjacent segments under strain.